lecture is the beginning of chapter 8, which is on roots and radicals. This is under 8.1 and 8.2 in your textbook. So the first part we want to talk about is about roots. So let's start off mentioning something that you probably already know this. For example, when we say a square root of 25, and we say that a square root of 25 is 5. And the reason why you say that is because when you take 5 and you square it, it gives you 25. Now, you notice 5 is not really the only choice because there is really another number that can do the same thing. So another square root of 25 is -5. And the reasoning is because -5, when you square it, also gives you 25. So, in summary, we say that the square roots of 25 are 5 and -5. So you notice there's really two answers. There's the positive answer and the negative answer. Okay, so the 5 is what we call the positive square root. And being the positive square root, that's another way of saying is the principal square root. And this principal square root is given a special notation. So the special notation is where we use the radical symbol. And if you like, you could put a 2 there. And that's when you call it square root of 25. And that's 5. Okay, so if you wish to say it's -5, then you're going to have to use 25, but with a minus on the outside to mean it's the -5. So this symbol is specially meant for the positive square root only. Okay, so if it's 2, a lot of times we don't even write it. It's understood. So if you don't see a number, it really means square root. So note that the radical symbol, okay, the radical symbol, that's this one, is used to denote the positive or principal square root. So let's see if there's other numbers. Okay, let's say what is cube root of 27? What would you answer? So the way you have to ask yourself is what number when you cube it gives you 27? So what choice would that be? Okay, so you can think, oh, 3 times 3 times 3 will do the trick. So here, 3 cubed gives you 27. So cube root of 27 is what you call 3. Okay, similarly, if I have the fourth root, okay, fourth root of, say, 81, what would that answer be? So again, you have to ask yourself, what number raised to the power of 4 gives you 81? So 3 times 3 times 3 times 3. So fourth root of 81 is 3. Okay, so the index that you see down here, so this is what you call the root index. So in general, that number could be anything, but if you don't see any number there, it really means the square root. Okay, so that's when we say that this is called the nth root of A. So in particular, take note of something. What if this was square root and -25? What would this be? Okay, so equivalently, it's asking you what number square gives you -25. So you notice that there is no real answer that will do the trick. So that's when you say the answer is non-real. So similarly, if now I were to ask you negative 81, okay, so again I'm asking you, which number raised to the power of 4 gives you negative 81? So again, this is a big question mark. That's because it's non-real. So in general, if the root index is even, but the radicand, that's the number on the inside, is negative, the nth root is non-real. Okay. All right. Let's get some examples down. Can you find the value of? Let's see. Can you find the value of? Let's try this. Root 100. So it's like asking you what number square gives you 100. So that's 10. What if now I have 36, but I have a negative on the outside? Then root 36 is 6, okay, but the minus will stay. So the minus is put back. All right. What if now I were to say what's negative of 4 over 81? So you could think of it as root 4 over root 81. So that comes out to be root 2 over 9, negative. Okay. What if this time I have negative on the inside? And let's say to the 4th power. That's when you say it's non-real. Okay, so for the reason that we just mentioned above, because the index is even, and yet the radicand, that's the number on the inside, that's the radicand, and the one up there is called the root index. So based on what we mentioned here, if the root index is even and the radicand is negative, then the nth root is not real, which is what happened here. Okay, there's a special example I want to mention. What if this was square root of 0.09? Okay, so when you deal with decimals, you have to be a little bit more careful. Think about it as a fraction. So 0.09 is the same as 9 over 100. So root 9 over root 100 is the same as 3 over 10. So the answer is really 0.3. Okay, so now that you understand how to do square roots and cube roots in general, so the big question is, what about if I were to ask you square root of x to the power of 6, what is that equal to? So remember the rule of the game. When we ask you what is square root x to the 6, equivalently we're asking you what must I put into the parentheses so that when I square it gives me x to the power of 6. So you notice that the trick is you have to use x cubed and x cubed. So that's why the answer becomes x cubed, because x cubed when you square it gives you x6. So you notice when exponents come into play, they follow a new rule. It's half of the exponent. Okay, so whatever is the exponent, you take half. So take for example, if I have m to the power 10 and n to the power of, say, 14, then all you have to do is take half of 10, so it becomes m to the 5th, and n14 becomes n to the 7th. So when it deals with exponents, all you have to do is take half. So numbers take a chart, and so does exponents. Okay, so they have different rules. So let's see. Let's combine them together. 169, x to the 8, y to the 10, z to the power 20. 169, what times what gives you 169? The answer is 13. But when you deal with letters and exponents, what you do is you take half of the exponents. Okay, so x8 becomes x to the 4th, because half of 8 is 4. Y to the 10 becomes y to the 5th, and z to the 20 becomes z to the 10, and then you're done. Okay, so numbers, they follow a rule, and exponents, they take their own rule too. So let's give the formal name for what we've been using. This is called the product rule, which says that when you have two things that is to be multiplied in a radical, it could be the nth root. Equivalently, it's like taking them apart, and that's exactly what we did. Okay, so we look at them individually and we just put them together as the answer. So that rule is what you call product rule. And the other rule that we've also used is called the quotient rule, which says that when you have a division, equivalently, it's like you can peel them apart and deal with them separately before combining them again. Now, these are the two rules we'll be using, especially for example. If now I were to say, what is, say, y to the 25? Now, 25 is a perfect square, but it's not perfect in terms of exponent, because for exponents we have to take half of it. So the trick is you have to write this as 24 times 1, because 24 is even, okay? And then you have to think of your product rule where you peel them apart. And y to the 24 becomes y12 out of the radical, but the y stays in there. So it becomes part perfect and part imperfect. So this is something we use for numbers as well. Supposedly the number is 54. Okay, so you notice 54 is not a perfect square, but you can break down 54 as root 9 times root 6. So root 9 is what we call, so you can think of root 9 times root 6, and that's the same as 3 radical 6. So that's how we write the answer. It's going to be part perfect and part not. So let's try another example. What if this time there's a negative on the outside? Then just leave the negative alone. But 700 is like 100 times 7. So that's negative 10, which is out of the radical, but the 7 stays in the radical because that's the imperfect part. So let's piece together a collection of questions. Say, can you simplify? Okay, and say square root of 200, x to the 25th, y to the 16, and z to the 11th power. Okay, so let's break them into what's perfect and what's not. So like 200, for example. You can break down 200 as 100 times 2, because 100 is perfect, as in root 100 is 10. Okay, x25 to the power 25, we're going to have to do it as 24 and 1, because we need it to be even. Y to the 16 is even, the exponent is even, so that's good enough. And z11th, I have to break it as 10 and 1. So what is not even, I have to break it. That's for exponents. Okay, so I'm going down the line. Root 100 is what we call 10. Root 2 is imperfect. I'm circling it, as in I'll deal with it later. X to the 24th, when I take half of it, becomes x to the 12th. X1 is imperfect. I'm going to deal with it. Y to the 16 is going to be y to the 8th. And z to the 10 is z to the 5th. And z is imperfect. So all the imperfect ones, I'm going to put them into a radical, and it's going to read 2xz. So the same applies if there's division involved. For example, if you're asked to simplify, for example, square root 96, x to the 3rd over z to the 16. Okay, so 96, let's break it down. 96, you could think of it as 3 and 32, which is useless. I'm going to break this 32 down as 2 and 16. So 16 is perfect. And the 3 and 2, I can combine it. So I'm going to write it as 16 times 6. X cubed is imperfect, so I'm going to break it as x squared and x1. So remember, exponents, you always need even. Okay, and z to the 16, that's even, so that's fine. Alright, so let's go down the line. 16 is 4. 6 is imperfect, stays. X squared is x. Okay, and x is imperfect. So what is in the square root is going to be 6x. And z to the 16, remember the rule is to take half. So that's why z to the 8th power. Okay, now that you understand how to simplify radical, let's introduce you to 3 different words. One is rational, what is irrational, and what's non-real. Okay, let's talk about non-real. Non-real, I think I've mentioned to you, usually it happens when you have an even index, like a 4, okay, and the radicand inside is a negative, like this, negative 16, that's non-real. So things like square root of negative 25, that's not real. Okay, 6th root of negative 100, that's not real. So long as it's an even index with a negative radicand, is non-real. Okay, so that's your non-real collection. For rationals, what happens is they are actually numbers that can be expressed as a over b, and a, b being integers, b not 0. What is included in rationals? They could be fractions. Okay, so for example, negative 2/5, that's rational. 4, that's 4 over 1, so that's rational. Even 0, 0 over 10, that's rational. Square root of 16 is 4, which is 4 over 1, so that's rational. 4th root of 81, that's 3, which is 3 over 1, so that's rational. Negative 2.5, which is the same as negative 5 over 2, so that's rational. So the list seems to keep going on. Okay, so really, rationals are numbers that can be expressed as a fraction, something over something, and that really includes decimals too. Like for example, 0.25, we can write it as 25 over 100. Okay, so it seems like everybody is irrational. So are there any irrationals then? So what are irrationals? Okay, so examples of irrationals would be like some of the ones that we've seen, like root 200. You notice that root 200 is made out of what's perfect and what's not. So the not perfect portion is what makes it irrational. Because if you were to press this on a calculator, it's not going to be a number that stops. It actually continues, and it doesn't continue with a pattern. Okay, it goes on without a pattern. So other examples would be like root 2, for example, cube root of 2, square root of 5, okay, negative 4th root of 10. So these are, if you were to press on the calculator, it's just going to be a decimal that continues. And one of them that you've seen in geometry, pi. Okay, that's irrational too. Let's look at the list of numbers and let's classify them as rationals, irrationals, or non-reals. Okay, so let's have a list of numbers. Say cube root of 27, square root of 18, square root of negative 25, 4 over 49 square root. Let's say cube root of 8 over 20. Let's say negative root 25. And let's say square root of 1 over 16 negative. Okay, let's try that. So what is considered to be rational? What's irrational? And what's not real? Okay, so cube root of 27 actually falls under rational because this answer is 3, which is 3 over 1, so that's rational. Square root of 18 is what you call irrational because it's not perfect. Okay, and square root of negative 25 is what you call non-real. Square root of 4 over 49 is actually 2 over 7, so that's rational. Cube root of 8 over 20. You notice you're supposed to look at it as cube root of 8 and cube root of 20. Cube root of 8 is a nice number, okay, but not cube root of 20, so that's why it's irrational. Negative root 25 is the same as negative 5, which is negative 5 over 1, so that's rational. And negative square root 1 over 16 is negative 1 over 4, so that's rational too. Okay, so there you have the classifications. Alright, the last thing that you need to know in these two sections, 8.1 and 8.2, is an application. And what this application does is it's something that you have seen before. It's called Pythagorean theorem. And what it does, it applies only to right triangles. It's a theorem that connects the three sides of a right triangle. So in a right triangle, there is an angle that's 90 degrees, and right across it is what we call the hypotenuse. And these two other sides are called the legs. Okay, so generally we use C to represent the hypotenuse, and the legs are your A's and B's. The only thing is, if you memorize the theorem as A squared plus B squared equals C squared, then a lot of times you get stuck, because I mean the question given to you, you hardly ever see the A, B, and C. Okay, so the safest way to do a problem is to identify the hypotenuse first. So take, for example, I draw you some funny triangle, but there's a right angle there. And I tell you that, say, one side is 6 and the other side is 12. And I'm asking you for the missing side. Okay, so you notice A, B, and C is not there, but the 90 degrees is. So that tells you you have to use Pythagorean and identify who the hypotenuse is. So right across the 90 degrees, that's the hypotenuse. Okay, so that's the one that's going to be alone. Alone as in on one side of the equal sign. So you have your two legs, square them and add them, and it's equals to the square of the hypotenuse. So you have x squared plus 36 is equals to 144. And when we subtract 36 on both sides, tells us x squared is 108. And then when you square root both sides, it tells you x is square root of 108. And this is where you apply what you just learned. 108 can be broken down. I can divide by 4, which makes it 27. And 27 I can break down some more as 9 and 3. 4 is a good number because it's a perfect square, so is 9. So the two perfect squares, you can put them together. 9 times 4 is what you call 36, which is perfect again. So this is going to be square root of 36 times 3, so that's 6 radical 3 is my answer.